In computer programming, a string is traditionally a sequence of characters either as a literal constant or as some kind of variable. The latter may allow its elements to be mutated and the length changed, or it may be fixed. A string is generally understood as a data type and is often implemented as an array of bytes that stores a sequence of elements, typically characters, using some character encoding. A string may also denote more general arrays or other sequence data types and structures. Depending on programming language and precise data type used, a variable declared to be a string may either cause storage in memory to be statically allocated for a predetermined maximum length or employ dynamic allocation to allow it to hold variable number of elements. When a string appears literally in source code, it is known as a string literal. In formal languages, which are used in mathematical logic and theoretical computer science, a string is a finite sequence of symbols that are chosen from a set called an alphabet. Formal theory. Let I pound be a non-empty finite set of symbols, called the alphabet. No assumption is made about the nature of the symbols. A string over I pound is any finite sequence of symbols from I pound. For example, if I pound equals 0, A1, then 01011 is a string over I pound. The length of a string S is the number of symbols in S and can be any non-negative integer. It is often denoted as S. The empty string is the unique string over I pound of length 0, and is denoted I micron or I. The set of all strings over I pound of length n is denoted I pound n. For example, if I pound equals 0, 1, then I 2 pounds equals 00, 01, 10, 11. Note that I 0 pounds equals a micron for any alphabet I pound. The set of all strings over I pound of any length is the clean closure of I pound and is denoted I pound. In terms of I pound n. For example, if I pound equals 0, 1, then I pound equals a micron, 0, 1, 00, 01, 10, 11, 000, 001, 010, 011. Although the set I pound itself is countably infinite, each element of I pound is a string of finite length. A set of strings over I pound is called a formal language over I pound. For example, if I pound equals 0, 1, the set of strings with an even number of zeros, I micron, 1, 00, 11, 001, 010, 100, 111, 0000, 0011, 0101, 0110, 1001, 1010, 1100, 1111. Is a formal language over I pound. Concatenation and substrings. Concatenation is an important binary operation on I pound. For any two strings S and T in I pound, their concatenation is defined as the sequence of symbols in S followed by the sequence of characters in T, and is denoted street. For example, if I pound equals a, B, Z, S equals bear, and T equals hug, then ST equals bayok and TS equals hugbear. String concatenation is an associative, but non-commutative operation. The empty string serves as the identity element. For any string S, I microsecond equals C micron equals S. Therefore, the set I pound and the concatenation operation form a monoid, the free monoid generated by I pound. In addition, the length function defines a monoid homomorphism from I pound to the non-negative integers. A string S is said to be a substring or factor of T if there exist strings U and V such that T equals USV. The relation is a substring of defines a partial order on I pound, the least element of which is the empty string. Prefixes and suffixes. A string S is said to be a prefix of T if there exists a string U such that T equals SU. If U is non-empty, S is said to be a proper prefix of T. Symmetrically, a string S is said to be a suffix of T if there exists a string U such that T equals US. If U is non-empty, S is said to be a proper suffix of T. Suffixes and prefixes are substrings of T. Both the relations is a prefix of, and is a suffix of a prefix orders. Rotations. A string S equals UV is said to be a rotation of T if T equals VU. For example, if I pound equals 0, 1 the string 00110001 is a rotation of 010010, where U equals 00 and 10 and B equals 01. Reversal, the reverse of a string is a string with the same symbols but in reverse order. For example, if S equals ABC, then the reverse of S is K bar. A string that is the reverse of itself is called a palindrome, which also includes the empty string and all strings of length 1. Lexicographical ordering, it is often useful to define an ordering on a set of strings. If the alphabet I# has a total order, one can define a total order on I# called lexicographical order. For example, if I# equals 0, 1 and 0 less than 1, then the lexicographical order on I# includes the relationships I micron 0 less than 00 less than 000. 0001 less than 001 less than 01 less than 010 less than 011 less than 0110 less than 01111 less than 1 less than 10 less than 100 less than 101 less than 111 less than 1111 less than 11111. The lexicographical order is total if the alphabetical order is, but isn't well founded for any non-trivial alphabet, even if the alphabetical order is. See shortlex for an alternative string ordering that preserves well-foundedness. String operations, a number of additional operations on strings commonly occur in the formal theory. These are given in the article on string operations. Topology. Strings admit the following interpretation as nodes on a graph. Fixed-length strings can be viewed as nodes on a hypercube, variable-length strings can be viewed as nodes on the K tree, where K is the number of symbols in I#. Infinite strings can be viewed as infinite paths on the K tree. The natural topology on the set of fixed-length strings or variable-length strings is the discrete topology, but the natural topology on the set of infinite strings is the limit topology, viewing the set of infinite strings as the inverse limit of the sets of finite strings. This is the construction used for the p-adic numbers and some constructions of the Cantor set, and yields the same topology. Isomorphisms between string representations of topologies can be found by normalizing according to the lexicographically minimal string rotation. String datatypes. A string datatype is a datatype modeled on the idea of a formal string. Strings are such an important and useful datatype that they are implemented in nearly every programming language. In some languages they are available as primitive types and in others as composite types. The syntax of most high-level programming languages allows for a string, usually quoted in some way, to represent an instance of a string datatype. Such a meta-string is called a literal or string literal. String length. Although formal strings can have an arbitrary length, the length of strings in real languages is often constrained to an artificial maximum. In general, there are two types of string datatypes: fixed-length strings, which have a fixed maximum length and which use the same amount of memory whether this maximum is reached or not, and variable-length strings, whose length is not arbitrarily fixed and which use varying amounts of memory depending on their actual size. Most strings in modern programming languages are variable-length strings. Despite the name, even variable-length strings are limited in length, although, in general, the limit depends only on the amount of memory available. The string length can be stored as a separate integer or implicitly through a termination character, usually a character value with all bits 0. See also null terminated below. Character encoding. String datatypes have historically allocated 1 byte per character, and, although the exact character set varied by region, character encodings were similar enough that programmers could often get away with ignoring this, since characters a program treated specially were in the same place in all the encodings a program would encounter. These character sets were typically based on ASCII or IBGDIC. Logographic languages such as Chinese, Japanese, and Korean need far more than 256 characters for reasonable representation. The normal solutions involved keeping single-byte representations for ASCII and using 2-byte representations for CJK ideographs. Use of these with existing code led to problems with matching and cutting of strings, the severity of which depended on how the character encoding was designed. Some encodings such as the EUC family guarantee that a byte value in the ASCII range will represent only that ASCII character, making the encoding safe for systems that use those characters as field separators. Other encodings such as ISO 2022 and Shift-JIS do not make such guarantees, making matching on byte codes unsafe. These encodings also were not self-synchronizing, so that locating character boundaries required backing up to the start of a string, and pasting two strings together could result in corruption of the second string. Unicode has simplified the picture somewhat. Most programming languages now have a data type for Unicode strings. Unicode's preferred byte stream format UTF-8 is designed not to have the problems described above for older multibyte encodings. All UTF-8, UTF-16 and UTF-32 require the programmer to know that the fixed-sized code units are different than the characters. The main difficulty currently is incorrectly designed APIs that attempt to hide this difference. Implementations. Some languages like C++ implement strings as templates that can be used with any data type, but this is the exception, not the rule. Some languages, such as C++ and Ruby, normally allow the contents of a string to be changed after it has been created. These are termed mutable strings. In other languages, such as Java and Python, the value is fixed and a new string must be created if any alteration is to be made. These are termed immutable strings. Strings are typically implemented as arrays of bytes, characters, or code units, in order to allow fast access to individual units or substrings including characters when they have a fixed length. A few languages such as Haskell implement them as linked lists instead. Some languages, such as Prolog and Erlang, avoid implementing a dedicated string data type at all, instead adopting the convention of representing strings as lists of character codes. Representations of strings depend heavily on the choice of character repertoire and the method of character encoding. Older string implementations were designed to work with repertoire and encoding defined by ASCII, or more recent extensions like the ISO 8859 series. Modern implementations often use the extensive repertoire defined by Unicode along with a variety of complex encodings such as UTF-8 and UTF-16. The term byte string usually indicates a general-purpose string of bytes, rather than strings of only characters, strings of bits, or such. Byte strings often imply that bytes can take any value and any data can be stored as is, meaning that there should be no value interpreted as a termination value. Most string implementations are very similar to variable length arrays with the entries storing the character codes of corresponding characters. The principal difference is that, with certain encodings, a single logical character may take up more than one entry in the array. This happens for example with UTF-8, where single codes can take anywhere from 1 to 4 bytes, and single characters can take an arbitrary number of codes. In these cases, the logical length of the string differs from the logical length of the array. UTF-32 avoids the first part of the problem. Null terminated. The length of a string can be stored implicitly by using a special terminating character. Often this is the null character, which has all bit 0, a convention used and perpetuated by the popular C programming language. Hence, this representation is commonly referred to as C-string. In terminated strings, the terminating code is not an allowable character in any string. Strings with length field do not have this limitation and can also store arbitrary binary data. In C, two things are needed to handle binary data: a character pointer and the length of the data. An example of a null terminated string stored in a 10-byte buffer, along with its ASCII representation as 8-bit hexadecimal numbers is, the length of the string in the above example, Frank, is 5 characters, but it occupies 6 bytes. Characters after the terminator do not form part of the representation. They may be either part of another string or just garbage. Length prefixed. The length of a string can also be stored explicitly, for example by prefixing the string with the length as a byte value. As a consequence, some people call it a p-string. Storing the string length as byte limits the maximum string length to 255. To avoid such limitations, improved implementations of p-strings use 16, 32, or 64-bit words to store the string length. When the length field covers the address space, strings are limited only by the available memory. Here is the equivalent Pascal string stored in a 10-byte buffer, along with its ASCII/UTF-8 representation. Strings as records. Many languages, including object-oriented ones, implement strings as records in a structure like. Although this implementation is hidden, and accessed through member functions, the text will be a dynamically allocated memory area, that might be expanded if needed. See also string. Linked list. Both character termination and length codes limit strings. For example, C character arrays that contain null characters cannot be handled directly by C string library functions. Strings using a length code are limited to the maximum value of the length code. Both of these limitations can be overcome by clever programming, of course, but such workarounds are by definition not standard. Rough equivalents of the C termination method have historically appeared in both hardware and software. For example, data processing machines like the IBM 1401 used a special word mark bit to delimit strings at the left, where the operation would start at the right. This meant that, while the IBM 1401 had a 7-bit word in reality, almost no one ever thought to use this as a feature, and override the assignment of the 7th bit to handle ASCII codes. It is possible to create data structures and functions that manipulate them that do not have the problems associated with character termination and can in principle overcome length code bounds. It is also possible to optimize the string represented using techniques from run-length encoding and Hamming encoding. While these representations are common, others are possible. Using ropes makes certain string operations, such as insertions, deletions, and concatenations more efficient. Security concerns. The differing memory layout and storage requirements of strings can affect the security of the program accessing the string data. String representations requiring a terminating character are commonly susceptible to buffer overflow problems if the terminating character is not present, caused by a coding error or an attacker deliberately altering the data. String representations adopting a separate length field are also susceptible if the length can be manipulated. In such cases, program code accessing the string data requires bounds checking to ensure that it does not inadvertently access or change data outside of the string memory limits. String data is frequently obtained from user input to a program. As such, it is the responsibility of the program to validate the string to ensure that it represents the expected format. Performing limited or no validation of user input can cause a program to be vulnerable to code injection attacks. Text file strings. In computer-readable text files, for example programming language source files or configuration files, strings can be represented. The NUL byte is normally not used as terminator since that does not correspond to the ASCII text standard, and the length is usually not stored, since the file should be human editable without bugs. Two common representations are, surrounded by quotation marks, used by most programming languages. To be able to include quotation marks, new line characters etc., escape sequences are often available, usually using the / character. Terminated by a new line sequence, for example in Windows INI files. Non-text strings. While character strings are very common uses of strings, a string in computer science may refer generically to any sequence of homogeneously typed data. A string of bits or bytes, for example, may be used to represent non-textual binary data retrieved from a communications medium. This data may or may not be represented by a string-specific data type, depending on the needs of the application, the desire of the programmer, and the capabilities of the programming language being used. If the programming language's string implementation is not 8-bit clean, data corruption may ensue. String processing algorithms. There are many algorithms for processing strings, each with various trade-offs. Some categories of algorithms include, string searching algorithms for finding a given substring or pattern, string manipulation algorithms, sorting algorithms, regular expression algorithms, parsing a string, sequence mining. Advanced string algorithms often employ complex mechanisms and data structures, among them suffix trees and finite state machines. The name stringology was coined in 1984 by computer scientists Vigalo for the issue of algorithms and data structures used for string processing. Character string-oriented languages and utilities. Character strings are such a useful data type that several languages have been designed in order to make string processing applications easy to write. Examples include the following languages: Awk, Icon, Mumps, Perl, Regs, Ruby, Sed, Snabel, TCL, TTM. Many Unix utilities perform simple string manipulations and can be used to easily program some powerful string processing algorithms. Files and finite streams may be viewed as strings. Some APIs like Multimedia Control Interface, Embedded SQL or PRINTF use strings to hold commands that will be interpreted. Recent scripting programming languages, including Perl, Python, Ruby, and TCL employ regular expressions to facilitate text operations. Some languages such as Perl and Ruby support string interpolation, which permits arbitrary expressions to be evaluated and included in string literals. Character string functions. String functions are used to manipulate a string or change or edit the contents of a string. They also are used to query information about a string. They are usually used within the context of a computer programming language. The most basic example of a string function is the function that returns the length of a string and does not modify the string. This function is often named length or len. For example, length, hello world would return 11. String buffers. In some programming languages, a string buffer is an alternative to a string. It has the ability to be altered through adding or appending, whereas a string is normally fixed or immutable. In Java, theory, Java's standard way to handle text is to use its string class. Any given string in Java is an immutable object, which means its state cannot be changed. A string has an array of characters. Whenever a string must be manipulated, any changes require the creation of a new string. This happens even if the original string's value or intermediate strings used for the manipulation are not kept. Java provides an alternate class for string manipulation, called a string buffer. A string buffer, like a string, has an array to hold characters. It, however, is mutable. Its array of characters is not necessarily completely filled. Thus, it has the capability to add, remove, or change its state without creating a new object. The exception to this is when its array is no longer of suitable length to hold its content. In this case, it is required to create a new array, and copy contents. For these reasons, Java would handle an expression like this. Implications. Generally, a string buffer is more efficient than a string in string handling. However, this is not necessarily the case, since a string buffer will be required to recreate its character array when it runs out of space. Theoretically, this is possible to happen the same number of times as a new string would be required, although this is unlikely. Either way, the effect is not noticeable in modern desktop computers. As well, the shortcomings of arrays are inherent in a string buffer. In order to insert or remove characters at arbitrary positions, whole sections of arrays must be moved. The method by which a string buffer is attractive in an environment with low processing power takes this ability by using too much memory, which is likely also at a premium in this environment. This point, however, is trivial, considering the space required for creating many instances of strings in order to process them. As well, the string buffer can be optimized to waste as little memory as possible. The string builder class, introduced in J2SE 5.0, differs from string buffer in that it is unsynchronized. When only a single thread at a time will access the object, using a string builder processes more efficiently than using a string buffer. String buffer and string builder are included in the Java Lang package. In .NET, Microsoft's .NET framework has a string builder class in its base class library. In other languages, in C++ and Ruby, the standard string class is already mutable, with the ability to change the contents and append strings, etc., so a separate mutable string class is unnecessary. In Objective-C, thin's mutable string class is the mutable version of the NSSTRING class. See also, formal language a set of strings in theoretical computer science, connection string a passed to a driver to initiate a connection, for example to a database, rope a data structure for efficiently manipulating long strings, bit string a string of binary digits, binary safe a property of string manipulating functions treating their input as raw data stream, improper input validation a type of software security vulnerability particularly relevant for user-given strings, incompressible string a string that cannot be compressed by any algorithm, empty string its properties and representation in programming languages, string metric notions of similarity between strings, string overview of C++ string handling, string overview of C string handling, analysis of algorithms determining time and storage needed by a particular algorithm, references. External links, the Java docs of String Buffer, String Builder and String Urban Performance Legends, an article which involves a discussion of immutable objects with respect to object-oriented design, string functions in PHP.